Laplace equation in the polar coordinates. So given these equations, so this is used for circular membranes, cylinders, and electrostatics around wires. So we have the example here of the solutions. U as a function of r and the angle theta here is equal to this equation a sub 0 plus b sub 0 ln r, and the product of these expressions r sub n a sub n plus r raised to the negative n bn parenthesis cosine of the n theta. So derive this formula cosine u as a function of r and the angle here. So let us derive this. So this is the general solution of Laplace equation in two dimensions, polar coordinates. So let us start with the Laplace equation in polar coordinates here. So we start with this. So we have this separation of variables. So a solution of the form u as a function of r and the angle is equal to the product of r and the angle here, product of the capital letter r and the capital theta. So r times the angle. So substitute into the Laplace equation here. Okay, so multiply by r squared, multiply through by r squared. So we have this. Then separation, a constant that the theta double prime is equal to negative n squared. So n here is an element of the integer. So we have to OD is here. So theta double prime plus n squared times the theta here equal to 0. So the solution of this is given by c sub n cosine n theta plus d sub n sine n theta here. So the radial part here is the solution of the radial part. The radial part here is r squared times r double prime of the capital letter R plus small r times the capital letter R prime minus n squared times r times minus n squared times r of r here equal to 0. So let us solve for the radial equations. This is an Euler type equations. So let us try r of r here is equal to r to the k. So substitution gives k squared minus n squared times r to the k equal to 0. So it means that k here is equal to positive negative n. So our solution for r here is r is equal to e sub n r to the n plus b sub n r to the negative n. So for n equal to 0, the radial equation becomes this. So r of r e sub 0 plus b sub 0 ln r. So we have the notes here. So if we are going to solve this, so the differential of r and capital letter R prime here is equal to 0. This one. So this one is the differential of R and R double R prime. So it means that R prime is equal to the constant. So the dr now is equal to c sub 0 equal to c sub 0 over r dr. So it means that the R is equal to c sub 0 times ln r plus c1. So the general solution is this one. So we combine the product of the r and the angle theta here. So the angle theta is equal to this, and the angle and the solution for the radial solution. The radial solution here is this one. E sub n r times r to the n, b sub n r to the negative n here, this one. So we have the, by using n equal to 0 here, so we have this expression. So if we restrict to cosine terms as in your formula, we get this uh, formula. So we reduce this to, uh, we just we remove the sine function here because the cosine is symmetry. So we use the cosine of the n theta because of symmetry. So what symmetry are we talking about? So the symmetry is u of r negative angle is equal to u of r positive angle. So we have the same value here. We have the same expression for the same solution for positive or negative angle here. So this is mirror symmetry about the x-axis or any chosen reference axis. So where does this symmetry come from? It comes from three things that are identical on both sides. So governing the equation is symmetric. So Laplace equation in polar coordinates is uh, this one given by this. So we have the physical interpretation here. For a geometric circle, eigenfunctions are cosine of the n theta, sine n theta. Radial dependence, power of r to the n and r to the negative n. The boundary data determines coefficient a sub n and b sub n. So we have here the solutions. That is what we have already derived. So this is the general solution of Laplace equation in polar coordinates. To see it in action, we'll pick a boundary condition and compute the coefficient. So the boundary condition here is, for example here, suppose we solve Laplace equations inside a circle of radius r equal to 1 with boundary condition here. So this means only the n equal to 2 cosine terms survive with a sub 2 equal to 1, all others 0. So the solution is this one. So we have the Mathematica simulation here. This is the plot of this solutions u of r and u as a function of r and the angle. So we have the explanation of the code here. So u of r theta, this defines the solution to the Laplace equation on a disk where r squared is radial part and cosine to theta is the angular basis functions. So we have the square root of x squared and y squared and the arctangent xy. Since Mathematica's contour plot usually operates in Cartesian xy coordinates, we transform the polar variables r and angle so the software can draw them on the standard grid. So we have the region functions here. So this restricts the plot to a circle of radius 1, the unit disk, which matches the boundary conditions. U as a function of the angle mentioned in your text. So color functions, we have the rainbow. This provides the multi-colored heat map visualization typical for these types of physics problem. So derivation of this uh, polar coordinates. So start from the Cartesian Laplacians. So into the Cartesians is equal to uh, the Laplacian of u is secant partial of u with respect to x plus the secant partial of u with respect to y. We have the chance of variable here. So polar coordinates are defined by x equal to r cosine of the angle, y equal to r sine of the angle. So u of x, y equal u as a function of x and y is equal to u as a function of r and the angle theta. First derivative here, so we have the derivative of u with respect to x equal to derivative of u with respect to r times the derivative of r with respect to x plus the derivative of u with respect to the angle. times the derivative of the angle with respect to x. So our r here is equal to the square root of x squared and y squared. So we have the partial of r with respect to x equal to cosine of the angle. We have the angle here is equal to arctangent of y and x, arctangent of y divided by x. So it means that the partial of the angle with respect to x is equal to negative r sine of the angle over r. Therefore, the partial of u with respect to x is equal to partial of u with respect to r times cosine of the angle minus 1 over r, partial of u with respect to the angle times sine. Now for the partial of u with respect to y, so using the same method here, we have the partial of u with respect to r times the sine of the angle plus 1 over r times the partial of u with respect to the angle cosine of the angle. Then we have the second derivative here, second derivative of u with respect to x here. So we have this. And so we have the partial of this, the partial of u with respect to y here. So we have another partial here. Okay. Then we have the explanation of this uh, double partial here. For example, here in x, let's find the partial of this with respect to x here. So we have this cosine of the angle times the partial of this uh, partial of u with respect to x here. So for example, let us first discuss this expression, the partial of this with respect to x. So how do we get this? So we have the partial angle here multiplied by the partial of r with respect to r here. So the double partial here, urr, times cosine equal to cosine squared minus 1 over r times uh, cosine times cosine times cosine times sine here. We have the explanation here. So the explanation here is given in here. So we have the partial of sine of the angle times the partial of this partial of u r sine of the angle. So this we have this double partial, the second partial of u with respect to r here. Then we have sine times sine here equal to sine squared. Then we have the next one here is 1 over r times the partial of u with respect to the angle here times sine. So we have this. So we have the 1 over r here times sine of the angle. Then the partial of times the cosine here. So sine times cosine times uh, partial view with respect to r and the angle here. So we have here the partial of u with respect to the angle and the partial of that with respect to r. So we have this. Then the next one is the partial of r with respect, the partial of 1 over r with respect to r. So that is negative 1 over r squared. Then multiplied by partial of u with respect to the angle here. Then multiply the sine and cosine here. This one. Then the next one here is uh, multiply uh, this one. So negative sine of the angle over r times the partial of this. So we have Hello, we have here the this term multiplied by this 1 over. So we have this cosine. So this term cosine over r times this terms, no? So cosine of the angle over r here multiplied the u sub r sine of the angle. So we have there cosine over r times cosine of the angle over r times u sub r times the uh, partial of the sine with respect to the partial of sine here is equal to cosine. And we have the cosine here, cosine of the angle here over r times the sine here. The partial of this u of r with respect to the angle. So we have the partial of r with respect to the angle here. So partial of u with respect to r and the angle. So by simplifying, so we have this term. Then this one, so multiply this term here, and this one over r, u cosine of the angle. So we have 1 over r squared. Then we have the cosine here. So we have cosine and partial of the cosine is equal to negative sine here. Then we have the u here, u the partial of u with respect to the angle. Then the next one here is 1 over r squared times cosine times cosine of the angle times the partial of the u here with respect to the angle. So we have the u here with respect to uh, the second partial of u with respect to the angle here. So we uh, we simplify this. So the sum of all this is equal to these expressions. This one. Then we have the u sub x here. So this is our explanation for the u sub x here. For example, here we multiply uh, this expressions. So this is the result here. So we also multiply the negative sign over r here, the partial of this expression with respect to the angle. We have the sum of u x x and u sub y y. So this is the u the second partial of u with respect to y here. We have the partial of x here, partial of u with this second partial of u with respect to x here. Then we add here the u sub x x and u sub y y. So we have the cancellation of the terms here. The mixed terms cancel. For example, here, uh, URR cosine here plus URR sine squared here. So the uh, cosine squared plus sine squared here is equal to 1. So we have the remaining term here. Then we have the cancellation here of the UR angle. So the partial of u with respect to the r and the angle here. So we have a cancellation. So this one also. So this one and so what are the cancelled here? So this one also cancelled, and this is also cancelled, and this one is this is equal to 1 over r squared. Uh, so double angle here. So this sine squared plus uh, double angle here plus cosine squared equal to 1. So we have 1 over r squared, the remaining one. So the remaining expression is u u sub r here over r. Okay, so this one. So what in divergence? So this expression is also equal to this. So this uh, so this one is equal to this. So this is this is our Laplacian of u here. So this one is equal to this. Then the last term here, 1 over r squared, the secant partial of u with respect to the angle. So this one also. So final Laplace equation in polar coordinates. So this is our final Laplace equations. So relation to Poisson equations. So if this is equal to 0, there's no sources here, no sinks. So if this is equal to f, uh, we have the Poisson equation here with sources. So we have an example here. For example, in the plus equations, if it is equal to 0, so the gravity outside the Earth here. So if we have the gravity inside the Earth, so it becomes the Poisson equations here. So we have example here of the uh, Laplace, for example, x squared minus y squared. So this is an example of the harmonic functions. So uxx, the partial of u, the second partial of u with respect to x equal to 2, and the second partial of u with respect to y here is equal to negative 2. So the sum here is equal to 0.